All right, so today we're going to start with counting techniques in probability problems. So the last class we learned about probability and about equal outcomes and everything like that. And today we're going to learn about how we can use counting techniques to solve probability. So we can use a lot of these like casework, complementary counting, etc. in probability questions. So here's a example problem. 10 people are sitting around the table. 3 people are selected at random. What is the probability that they are sitting next to each other? So basically in this problem, we have 3 people who are selected at random from 10 people around the table. And we have the possibilities that they're going to be next to each other. So basically in this problem, we should counter outcomes as the ways to solve 3 problems without caring about order. So then basically how we find probability is we have to find the number of successful outcomes out of the number of total outcomes. So first we find the number of total outcomes. So we do 10 choose 3 to find how many ways we can choose 3 out of 10 people. So that would be 10. That would be 10 factorial divided by 7 factorial and 3 factorial. And then that would be 10 times 9 times 8 over 3 times 2 times 1. We can cancel this out and we get 120. So 120 is the number of possible outcomes there are, but now we need to find the number of outcomes that actually work and number of outcomes where we have 3 people right next to each other. And there are only 10 ways to choose 3 people right next to each other, since if you have 10 people sitting around the table, there are 10 ways to choose the middle person and then the 2 people around them. So then there would be 10 people. 10 ways to choose 3 people who are right next to each other. So then 10 divided by 120 equals 1 out of 12. So then that's the probability that if you choose 3 random people, they're going to all be sitting right next to each other. All right, so I have 2 practice problems here. I'll give you guys a few moments to do these. So if you have any questions, you can message me. When you guys are finished, can you DM, can you private message Ethan, the host, because I've only received one answer so far, and I need to know you guys are keeping up with the problems. All right. So basically, every card deck has 13 of each suit. So like a suit is the thing that is on the card, like the diamonds or the clubs. So there's 13 of each suit, and then each rank has 4, and each card is like different. It has its own suit and its own rank. All right, I'll go over the first problem as of now, and I'll go over the second problem when I get more answers. So two different two-digit numbers are selected and multiplied. What's the probability that the product is even? So in this problem, an outcome is selecting two different two-digit numbers without regard to order. So first we need to find the number of possible ways we can choose two different two-digit numbers. So there are 90 two-digit numbers, right? From 10 to 99, there's 90 of them. So we need to find how many ways we can choose 2 from 90. And then we do this and we get 4005. But now we need to count the number of successful outcomes and then divide that by the number of possible outcomes. So here, we know that two numbers multiply together to get an even number if at least one of the original numbers is even. So that means that only one of the numbers has to be even if the product is going to be even. Like if you have an odd or an even number, the product will still be even. So two numbers multiply together to get an even number. To count this, we will need some casework. And we could use casework if we have like two even, one odd, and one even. But we can also use complementary counting here, which is where we count what we don't want to count. And it's easier when the product of two numbers is odd. So we just need to count all of the possibilities where both of the numbers are odd. So there are 45 odd two-digit numbers. So like 11, 13, all the way. Well, we're not dividing 4005 by 2 since we just did choose 2 from 90. So we're already not counting the order. So now we're going to use complementary counting to count all of the cases where the product would be odd. So we're going to choose 2 from 45, and this would end up being 990. Oops, 990. So now what we do is we subtract 990 from 4005 to find the number of ways we can count all the even numbers. So we just do 4005 minus 990, which is 3015. Now we just find the probability, so it's 3015 over 4005, which is equal to 67 over 89. So this is the answer to the first one. All right, so now I'm going to go over the second one. We have a deck of 52 cards. We call a 5-card poker hand a full house if the hand has 3 cards of one rank, like the number or title, like aces or threes. You know, like every card is like an ace, 2, 3, 4, 5, like jacks, kings, and all that stuff, and 2 of another rank. So what is the probability that 5 cards chosen at random will be a full house? So this one's pretty hard. So first what we do is we find the total number of possible outcomes. So we just choose 5 from 52. And what we'll get is 2,598, 2,598,960. So what we do now is we need to count the number of ways we can choose a full house. But here we need to turn to constructive counting. And to form a full house, we need to choose a rank for the 3 cards. So since there are 13 ranks, there could be 13 ways. So we just do 13 times. And 3 of the 4 cards of that one rank. So we choose 3 from 4, and we can do that 4 ways. Times a rank for the other 2 cards. And since one of the ranks is already used, we have 12 ways. And 2 of the 4 cards of the other rank, and we choose 2 from 4, we can get 6. So then the number of possible full houses is 3,744. And we just divide that by whatever we just got. And then we find the answer is 6 over 4,165. So this one's pretty hard to figure out, but the key thing here is you need to use the counting techniques you know how to do in order to find the number of possibilities for everything. All right, so I have some more simple, more straightforward exercises, and if you know the answer, you can message me. And if you don't know how to do it, just tell me I don't know how to do it, and I'll explain it once everyone's done. Oh yeah, 1 to 100 is inclusive. Alright, so I'll go explain all of these problems. So these should be more simple than the ones that we just went through. So here we go. A box contains 5 white balls and 6 black balls. What's the probability of a ball being drawn out that is white? So since we know that there are 5 successful outcomes where we pick a white ball and 11 total outcomes where we don't, it doesn't matter what color is the ball we pick, that would just be 5 out of 11. So that's simple enough. Now we need to look at if 2 balls are drawn out, what is the probability that they are both white? So first we need to find the number of ways we can choose possible outcomes. So since we have 11 balls and we're choosing 2, we had to find all of the possible ways we can choose 2 from 11. So let me just do it down here. Choose 2 from 11, and we will get 55. And now we need to find the number of successful outcomes. So the problem's asking us for both of the balls being white. And we know there's 5 white balls, so we need to find the number of ways we can choose 2 from 5. So choose 2 from 5 is 10. Yeah, it's 10. And we divide the number of successful outcomes by the number of possible outcomes. So 10 out of 55 equals 2 out of 11. So yeah, that's the final answer for the second one. I'll just erase everything down here. And then 2 out of 11. If 5 balls are drawn, what is the probability they are all white? So this one, you know it's not going to be like very likely since there's only one way to choose all the white balls. This is using counting methods like complementary counting and all that stuff to find probability problems. And this is just practicing probability basically. If 5 balls are drawn, what's the probability that they are all white? So here we go. First, we need to find the number of ways we can choose 5 balls from 11, the number of possible outcomes. So choose 5 from 11. We will get 462. And since there's only 5 white balls, there's only one way to choose all 5 of the white balls. So we know the answer is going to be 1 out of 462 for the third one. All right. Now, the second part is a lot easier. What is the probability it's a perfect square? So from 1 to 100, first what we do, we find all of the perfect squares from 1 to 100. So basically, we just do this. So we can just find all the perfect squares, the number of successful outcomes. So we have 1, 4, 9, 16, blah, 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 all the way to 100. And now we can simplify this to 1 to 10. And we know there's 10 perfect squares since all these numbers are just the integers squared. But now we know the number of possible outcomes is 100. So 10 divided by 100 is 1 out of 10. So 1 out of 10 numbers is a perfect square. Next, we find the probability it's a multiple of 3. Again, this one's also pretty straightforward. There's 100 possible outcomes. There's 100 possible outcomes, and we have 33 multiples of 3. So it's just that, 33 out of 100. So the summary of this section is if all outcomes are equally likely, which we did last week, the probability of success in the number is the number of successful outcomes divided by the number of possible outcomes. And probability is always between 0 and 1. So if you get it larger than 1 or less than 0, you're doing it wrong. You need to count both outcomes with the same conditions. We can't count successful outcomes with order and possible outcomes without order. So basically they both have to be accounting for order or just no order. You can't have them doing different things. So yeah. Now we are going to move on to basic probability techniques. So in here we learned that many probability problems are counting problems, basically. And now we need to learn how to apply counting techniques to solve probability problems. So we're going to use our casework. We're going to use the complementary stuff, counting what we don't want, and we're going to use all this stuff. So when two events cannot happen together, they are called mutually exclusive. This is something you need to remember. So basically what mutually exclusive is like two things cannot happen together. So you could like say, what's the probability that a shirt is red or blue? Like it could either be red or blue. It's not going to be both red and blue. So yeah, that's mutually exclusive. So the demonstration problem, when rolling a fair six-sided die, what's the probability you roll a 2 or 4? So here we go. So there are there are 6 equally likely outcomes, and there are 2 successful outcomes, which is when you roll a 2 or 4. So then that would be 2 out of 6 or 1 out of 3. So that's simple. Notice that the probability of the roll being a 2 or 4 is equal to the probability of the roll being a 2 plus the roll being a 4. So that means that these are mutually exclusive events and they can't happen together. So basically the rule that we need to know here is the number of ways we can do one or the other is equal to the probability of one plus the probability of the other only if they're mutually exclusive. So that's something you should remember. All right, so I have some more exercises here for you guys. You can ask me anything if you have any questions. You can tell me the answers through a message, and I'll give you some time to do these. All right, so I'll be going over these right now. So first one is, I think it is pretty simple. So a coin is flipped 7 times. What's the probability that at least 5 of the flips are heads? So here, since there are multiple possibilities for the number of heads we get, so since it says at least 5, we can get 5, 6, or 7 heads. So we need to account for all of these, which is where we use casework. So first we need to count the number of ways we can get 5 heads. So in here we simply choose 5 from 7. So 5 heads, right? We choose 5 out of the 7 coins to be heads, and the number of ways we get here is going to be equal to it's going to be 21. And now we need to count the number of ways we can get 6 heads. We choose 6 from 7, and since there's 1 missing, there's going to be 7 ways. And 7 heads. Since all 7 of them are going to be heads, there's only 1 way to do this. So 21 plus 7 plus 1 is equal to 29. But now we need to find the number of possible outcomes. So since each coin has 2 possibilities, heads or tails, and there's 7 of them, the number of possible outcomes is 2 to the power of 7, which is 128. So now what we do is we simply divide 29 by 128, and that is our answer for the probability for the first question. 29, 28. All right, so that is our answer for the first one. Now the second one is a card is chosen at random from a deck of cards. What's the probability that the card is a queen, a diamond, or both? So as I told you earlier, there are going to be 4 queens and 13 diamonds in the deck. So what you might think is, well, since we have 4 queens and 13 diamonds, we add 4 plus 13, we get 17, right? But that's not the right answer. 17 is not the right answer because there is going to be 1 card that's both a queen and a diamond, and you're counting that twice. So that's going to be the AND region, right? Since these events are not mutually exclusive, you have to subtract the AND part, which is when both of the probabilities happen at the same time. And since there's 1 card that does this, we do 17 minus 1, and that would be 16. So 16 is the answer for the second one. All right. So now we have the third one. A bag is 3 red and K white marbles, where K is an unknown integer. 2 of the marbles are chosen at random. What's the probability that both marbles are white? So here we know that we have K white marbles, and we're choosing 2 from K. So that's going to be the number. We need to find the number of successful and the number of probable outcomes. Yeah, and remember that if you have a probability, it's always going to be between 0 and 1. Sometimes it's inclusive, but most of the time it's not. So in here, what we do is we are going to find the number of ways we can choose white. So since there's going to be K white marbles and we're choosing 2 from K, the number of successful outcomes is choose 2 from K to go. And the number of probable outcomes is going to be choose 2 from the total. Oh yeah, probability. There's 52 cards. That's divided by 52. It's just 4 out of 13. Yeah, my bad. So now we're just going to do the one we're doing now. So we're going to choose the number of possible outcomes now. So that's just choosing 2 from all of the cards. And that's going to be choose 2 from k plus 3 since there's 3 extra cards. So this would be the answer for what is the possibility that they're both white. Now we just see what's the possibility that both are red. So number of successful outcomes is the number of ways we choose 2 from 3. So 3, 2, that equals 3. So it's going to be 3 over the number of possible outcomes, which is again k plus 3 over 2. So yeah, that was supposed to be using the variable, and basically it's just the same concept but with a variable. So yeah. So what we learned here is we learned about mutually exclusive events. So the formula of the mutually exclusive events is if PA and PB are mutually exclusive, the probability of A or B happening is them added, or if we have multiple exclusive events, it's going to be all of them added. But if they're not mutually exclusive, P, A, or B is going to be PA plus PB, but we have to subtract PA and B since they're happening together and that region is being counted twice, so we have to subtract it from the total of PA plus PB. So yeah, that's the formula for mutually exclusive events and events that aren't mutually exclusive in probability. All right, so now we're going to learn about complementary probabilities. So in the last section, we learned about addition of probabilities for mutually exclusive events. So now we're going to look at a special kind of probability. What is P? What is the probability that it will rain tomorrow plus the probability that it will not rain tomorrow? So this is kind of a special case because you know that either way, it's going to either rain or not rain. There's no like in between or any other case. They're exclusive events. They can't both happen at the same time. So what we can say is since we're guaranteed that one or the other will happen, it's going to be 1. Since it's going to happen either way. So basically what the rule is that the probability that something does not occur is 1 minus the probability of that thing occurring. So that's a rule. So now I have basically this is complementary probability. We're counting what we don't want to count and then subtracting it from 1 to find the probability. All right, so let me go over these now. So here, what is the probability that if we roll 4 dice, they will not all be the same number? So here, counting the number of outcomes in which 4 6-sided dice don't all show the same number, this would require a lot of work. This would require a lot of effort. But what we do in complementary counting is we count what we don't want to count. So in this case, we would count the probability that they are all the same number. So basically in here, there's only 6 ways this could happen. They could either all be 1s, 2s, 3s, 4s, 5s, and 6. And then, so the number of successful outcomes would be 6. But now we need to find the number of probable outcomes, number of possible outcomes, which is 6 to the power 4. So 6 divided by 6 to the power 4 is 1 over 6 to the power 3, which is 1 over 216, which is the probability that they're all the same. But we're counting the probability of them not being the same. So we can use the rule that we just learned, where we subtract, where we find the probability of what 1 minus what occurs, something that actually occurred. So 1 minus 1 over 216 is 215 out of 216. So the second problem, if we roll 4 dice, what's the probability that at least 2 would be the same number? So here we can still count what we don't want to count. So we can find the probability that they're all going to be different numbers. Numerator is 6 because there's 6 possibilities for them all being the same number. So they could be 4 1s, 4 2s, 4 3s, and so on. So here we're going to count the number of ways we can have them all different. So we have 6. So we're going to do this in we're going to do this way. So there are 6 probabilities for the first one. There are 5 for the second, there's 4 for the third, and there's 3 for the fourth. And we multiply this all together. We are going to get, I think it's 360. And now we need to find the possibilities of all 4 of the possible outcomes. So 6 to the 4th power. And now we just divide 360 by 6 to the 4th power. And what we get is, we can just cancel this. We get 10 over 36, which is 5 over 18. But now we need to find the number of ways which this does not occur. So 1 minus 5 out of 18 is 13 out of 18. So that's the answer for the second one. So now we do this. The letters 16 are randomly arranged. What's the probability that the 2 E's are not next to each other? So here we're also going to use complementary counting, where we're going to find the probability that they are next to each other. So since they're next to each other and they're always going to be next to each other, we can count them both as one letter basically. So the number of successful outcomes, we would have like 6 different letters, S, I, X, T, N, and then the 2 E's together. So number of ways we can have arranged these 6 letters are 6 factorial over the number of total outcomes, which is 7 factorial, the number of ways we can randomly arrange those 7 letters. And what we get is we get 1 out of 7. So yeah, that's the answer for the third one. All right, so probability and multiplication. So exclusive events lead to the addition of cases. This is also true for probability. In counting, we saw how to deal with a series of independent events, like choosing shirts, pants, and shoes for an outfit, where we just multiplied the number of possibilities together. We can do this for probability too. So two six-sided dice, one red and one green are rolled. What's the probability that the red one rolls a 2 and the green one rolls a 5? So here we're going to calculate the probability for each die. So for the red one, the possibility that it's a 2 is going to be 1 out of 6. And for the green one, the possibility it rolls a 5 is also 1 out of 6. So we multiply these together and we get 1 out of 36. That's simple enough. Now I have two pretty quick practice problems, and I'll let you guys do these. And if you have any questions, you can ask me.
The dice are regular dice. Like, they have the numbers 1 through 6, right?
Also, if you're sending answers, can you please do it in private chat? Because if you do it in public chat, you're just giving the answer to other people. All right, so these are going to be the last problems we're going to go over for today. So 2 6-sided dice, 1 red and 1 green, are rolled. What is the probability that the red die has an odd number and the green die has a perfect square? So here we're going to have 2 separate die, and we're going to multiply the possibilities together to get our answer. So first we're going to see how many ways the red die can have an odd number. Since there's 3 odd numbers out of 6 numbers on the die, that would be 1/2 of a chance of an odd number times the possibility that the green die has a perfect square. So there's 2 perfect squares on a die, 1 and 4. So that means 2 out of 6 would be 1 out of 3. We do this, and then we multiply these together since they're happening together, and we get 1 out of 6. That's the answer for the first one. So the Grunners. So now we have the second problem. The Grunners play the Screamers 4 times. The Grunners are better and are 75% likely to win a game. What is the possibility that they will win all 4 of the games? So let's go. So what's wrong? So here we're gonna have a fake solution and then a real solution. So the fake solution is, since there's 2 possibilities for each game, there's going to be 16 possible outcomes. And since the Grunners win all 4 games, it's gonna be 1 out of 16. This is wrong since you didn't account for the 75%, and you need to account for that when you're solving it, and also the possibilities will not be equally likely. So instead we'll use multiplication of probabilities of independent events. Each of the 4 games is independent of the others, and each game the Grunners have probability 3 out of 4 winning. Therefore, we need to multiply 3 out of 4 4 times. So 3 out of 4 to the power of 4 is going to be 81 out of 256. All right, so that is it for today. I will see you guys next week. Bye.
Bye.
Hi, thank you.